Today we study chapter 3, gauge invariance and covariant derivative. To begin with, we study charged particle Lagrangian and Hamiltonian in the relativistic formalism. In the rest frame of a charged particle, the interaction Hamiltonian, interaction Lagrangian is minus potential, interaction potential. If the particle is at rest, it does not have magnetic interaction. It does have only electrostatic interaction. So we can introduce the potential phi, electrostatic potential phi, multiplied by the charge q of that particle. So let us find the Lagrangian invariant form of the Lagrangian for this charged particle system. Then this phi is actually the zeroth component of the 4-vector potential. And if we collect the zeroth component of this 4-vector potential, it is good to multiply for velocity in the rest frame of that particle. Because it is not moving, that u mu is just a c comma 0. So if we make a scalar product between u and a, then the result is just a c phi. So this phi can be rewritten as a c phi, and q is divided by c. Then we find the gauge invariant notation expression for this q phi. So q phi is the expression in the rest frame of the charged particle, but even if it is moving, there is some covariance of this 4-vector potential and 4 velocity to make this whole object a Lagrangian invariant. Let us recall the fact that the action, that is the integral over time of the Lagrangian, is invariant on the Lagrangian transformation. If we rewrite this integral over time in terms of gauge Lagrangian invariant quantity that is a proper time, then we find that gamma, Lagrangian boost factor multiplied by Lagrangian, must be Lagrangian invariant. So Lagrangian must be proportional to 1 over gamma multiplied by some Lagrangian invariant quantity. Therefore, because we have found that this guy is Lagrangian invariant, interaction Lagrangian must be of this kind of form. We recall that this one is exactly the same as this in the rest frame of the particle, because at that frame gamma equals 1. So we don't care whether gamma, we don't care about this gamma at that frame. But as soon as it is boosted to another frame, this whole object is a Lagrangian invariant, but there's over factor, boost factor appears. But happened to be in this rest frame, this gamma was 1, so this expression is the same as divided by gamma at that frame. That's the reason why we use interaction Lagrangian. General expression for the interaction Lagrangian is minus q over c u dot a divided by gamma. Let us recall the free particle Lagrangian for this particle, a massive particle with mass, rest mass m. Then Lagrangian for the free particle is a minus mc squared over gamma. Okay, if we sum this free particle Lagrangian and the charged particle Lagrangian, interaction Lagrangian due to the electromagnetic field, then the result is just the sum of this guy and this guy. And we have over a factor minus 1 over gamma multiplied by mc squared rest mass rest energy plus q over c u dot a. If we re-express this gamma, 1 over gamma, it is just square root 1 minus velocity squared divided by c squared. And we remember in the general expression for the moving frame, for velocity has over a factor gamma. That gamma cancels this gamma in the denominator to make the expression to be the minus q phi plus q, velocity over speed of light, dot vector potential. In order to find the Hamiltonian expression, so this is the expression for the charged particle Lagrangian, which is a relativistically covariant form. In order to find the Hamiltonian of this system, we have to find a conjugate momentum for the velocity of ith component. So let us take the derivative, partial derivative with respect to the velocity. Then the final result is this expression. Okay, velocity dependence, there is no velocity dependence, so this guy has velocity dependence, but this guy is removed, and the q over c dot a. So dot a is, if we take the ith derivative, I have, I missed this. This is ith component. So this guy is this, and if we take the derivative, what we find is this. Okay, if you take the derivative of the square root, it becomes this square root goes in the denominator to make this factor gamma, and you know, square root derivative of square root is 2 times square root, this kind of form. And I have factor of 2. If we take the derivative inside the square root, this factor of 2 cancels, and then negative sign cancels. So to make the final result like that. So what we find is, move this guy to the left hand side to find the capital P, that is conjugate momentum, subtracted by q over c, vector potential, divided by over vector gamma m. That is the velocity. We remember gamma is 1 over square root this factor. So this guy, gamma squared, and 1 minus velocity squared divided by velocity speed of light squared is just identity. And expand these guys. And let us make use of this factor, this result. Then I have gamma x dot. Okay, so gamma x dot squared can be expressed in terms of right hand side squared. So if we substitute that one in here, we get this result. So let us multiply m squared c squared to both sides, and this guy, it becomes mc squared, and move this one to the left hand side, that is p minus q over ca squared. And then this factor, this term becomes gamma mc squared. If we take the square root, sure we have positive mass only, so we have positive square root only. Then the final result for the gamma mc is the square root mc squared plus p minus q over ca squared. Alright, so gamma mc can be substituted in here to find the final result for the velocity over speed of light is, make use of this, we find p minus q over ca divided by square root. Alright, if we make use of this fact, then we're almost done. The Hamiltonian is by definition conjugate momentum, scalar product of conjugate momentum and velocity subtracted by the Lagrangian. Lagrangian is written here. If we copy this result in here, then we find this guy is this, and I have copied this one in here. You know, this square root is just 1 over gamma, so mc squared divided by gamma, and we flip the signs of the 3 terms, plus q phi and minus q velocity over c dot a. Okay, what we have to do is we have to remove these velocities. by making use of this relation. So after some calculation, the final result is Hamiltonian subtracted by q phi is subtracted, divided by speed of light, which has the dimensional momentum, is the square root mc squared plus p minus q over ca squared. Interesting thing here is that for the free particle, we had this kind of form. But even though we have a very long calculation, the final result can be obtained by a simple replacement, that the Hamiltonian is replaced by Hamiltonian subtracted by electrostatic energy, that is q phi, and momentum is replaced by conjugate momentum capital P subtracted by q over c vector potential. So even though we have done very long calculation, from here on we won't calculate again, and if we introduce a charged particle system, then what we have to do is just replace the free particle Hamiltonian by h minus q phi and free particle momentum by conjugate momentum subtracted by q over c vector potential. That's it.